So it's hello.
He's muted, I think.
Samson sir, hello.
Should we get started? Can you hear me? Hello? Okay, I'll get started.
Hello.
Yeah, can you hear me? I can't hear you. Can you guys hear me? See the dot there. Yeah, it's breaking now. Yes, we can. Okay, so I'll get started. Let me share my screen. And bring my presentation up here. So just 1 minute. Okay, I'll have to stop it here. The other screen. Okay. So you can see my screen. Can you see my screen, guys? Yes, we can. Okay. Okay. So, okay, my name is Sagar Deshpande. I am originally from Bombay, and I did my undergraduate in Bombay University, and then I was at IIT Kanpur. I did my master's in geoinformatics. So today, actually, today I'll be talking about alignment mapping of structural members and rollers in steel mill using terrestrial lidar point cloud. So this was one of the projects that I worked on while I was doing consulting over here. I was trying to help a company to solve their problems. They were like the pioneers in this particular field. They scan steel mills and basically provide solutions to the steel mill companies. So here's my background actually. So I'm originally from Bombay, as I said. I did my diploma in civil engineering first, and then followed by bachelor's in civil engineering from Mumbai University. Then IIT Kanpur, where I did my first master's. Then I came to Then for a year, actually, I was at IIT Bombay. That's where I met Nisha. She was a PhD fellow back then, and I was a research fellow. And then I moved to US. I did my master's again at Ohio State, and I also gained my PhD. While I was doing PhD, I was also working in the United States. So the other side, basically, where you see that I became a water resource engineer and mapping analyst. That was after my master's at Ohio State. And then I became assistant professor at Ferris State. And I was pursuing my PhD on the side. So in 2017, I got my PhD, and I was also associate professor at Ferris State. I used to do consulting. So I had a company called SNE Engineers, and I worked with three companies to basically provide technical advice and providing solutions for them. And one of them is the work that I'm going to present today. Followed by that, I also worked as associate professor at Penn State. And now currently, like past 2 years, I've been a senior geospatial technology manager at Dewberry. So that's my work since timeline basically since I left India. I'm going back. So first 10 slides, I'm actually giving an overview of what I've been doing. And then the remaining slides are based on the topic today. So originally, my very first geospatial project was my master's thesis at IIT Kanpur. And the title was deformation monitoring using close-range photogrammetry. And you can see a control field and targets placed on dial gauges. And I developed a lot of 5 methods actually to extract target automatically, semi-automatically, and then evaluated the accuracy of those target extraction methods. So my focus was primarily on automation and developing semi-automated techniques. So I will not go into much detail here. That's why I'm just going ahead. I'll get into details of newer topics. So this slide is, so at Ohio State, I was a full-time student for 3 years. And I was a research fellow over there also for 3 years, those 3 years. So during that time, I worked on different projects, several projects. And so this is kind of a summary of those projects. Integration of aerial and satellite imagery. So the figure on the side that you see here, you can see the base image is actually a QuickBird image followed by a Iconos image on top. And the white patch that you see is a is a bathymetric data along the shoreline that was available to us. Now I'm talking about 2006 time frame, and data availability at that time was not really great. And I mean, until now, I mean, it's like 2006 to 13, like 10-15 years, and things have changed drastically. So but my work here was basically merging of multi-sensor data. So Iconos with bird aerial images, I combined all of them and tested accuracies. So I'll talk about that in subsequent slide. And then I did bluff line extraction. I developed a method for bluff line extraction, so I'll also talk about that briefly. Correlation of local and regional factors for coastal erosion. That work was presented at ISPLS conference, and then development of a lot of tools. I mean, those 3 years I worked, like my research was really active, and I was really into a lot of things. So going a little bit detail on my work over there. So Iconos was a company, was a satellite that was owned by GeoEye, and they contacted us because we had a couple of, we means the university, because my program, my lab, actually research lab, published a couple of papers on Iconos. So they wanted to test convergence angle and accuracy for Iconos. So they contacted us, provided satellite images. So you see these stars on the sky plot here. That's where we got the imagery from Iconos or GeoEye, and we conducted testing of that area. Now, the area was Tampa Bay, Florida. We had a lot of control data set available, and that was the reason we were using them. So with conversion angle, we saw how things, wider convergence angle definitely increase the vertical accuracy. So that's what we observed here, and also X and Y accuracy variation, not significantly varying, but still a little bit of variation. The other work that I did was bluff line extraction. So bluffs are basically vertical features, and over in Ohio there was a lot of erosion. So the project was basically so the project was basically extracting these bluff accurately and semi-automatically there. So in here I had like transects laid perpendicular to the shoreline, and then we used 2 data sets. So the goal here was, how can we use horizontal mapping from orthophotos, whereas get the vertical from Lidar, because vertical Lidar is better than the horizontal. And ortho imagery, obviously there is no vertical to it. So over here we did segmentation to ortho images, surface reconstruction, and got 2D bluff lines. And Lidar data, we did a slope-based technique by which we could get the crest or the change in curvature at the top. And then we applied ICP algorithm to fit these 2 data sets. That is 2D from bluff line and 3D from the third dimension from the Lidar data. And then we got the refined line. We compared it with ground-based data, GPS observations, and reported the accuracy. Another one that I did at Ohio State, over here we had, you can see 3 tracks actually. The outer one is QuickBird, inner one here is Iconos, and the images itself, which are aerial images. Now, the thing here is the satellite geometry of Iconos and QuickBird, they were defined using rational polynomial coefficients. 78 parameters to define the orientation and like basically the complete parameters for the images. Now, the problem was that sensor geometry for aerial images basically our traditional focal length and different parameters for the, because these are frame-based cameras. So then how do we bring both of them in one system to perform the integration? So basically, we reprojected virtual points so that we can compute 78 parameters for each image. And then once all of these had the RCPs or RPCs, basically rational polynomial coefficients, then all the data was integrated and study was performed. So there's, you can see the dots here. These were our checks and control points. The triangles are control and the circles are check. Here's a description of how accuracy improved by adding. So we did like, a couple of combinations to study. So Icono stereo alone, followed by QuickBird stereo alone, and so on and so forth. So you can see that although we could do some changes, but really aerial images were still the best at that particular time. Now, I mean, things are changing rapidly. Moving on, this is my PhD thesis. So PhD thesis was based on Lidar data. So the problem here in Lidar data is that, like, not here, in general, Lidar data over water has basically uneven surface. And there's a lot of work or efforts to basically remove these features and show the water surface something like this. And this process is called as hydroflattening, where basically the elevation of the water surface slopes downward. And there are many more constraints and requirements that are laid down by USGs. Okay. So there's an example here. So on the left side, I'm trying to show that there is a creek here, which is practically not visible at all. But you can see the line going through it, the center line of the river. On this figure here is a lake or a pond. And again, same thing, you can see a lot of features inside, there are points inside. And so what I did here was I used two sensors. One is our linear mode, which is basically the traditional LiDAR, linear mode LiDAR. And the second data set was from single photon. So single photon or Geiger mode LiDAR is a different technology. And the point density is significantly high when compared to linear mode LiDAR. So I did, and the property is that the single photon works here. No, so that's the linear mode, sorry. One micrometer wavelength, and whereas the linear Geiger mode or single photon is somewhere here near green wavelength. And the property of green wavelength being it penetrates water surface. So now the linear mode basically is uncertain over water, whereas the single photon can penetrate water. So two different approaches were needed to be developed to perform hydroflattening. Primary goal was basically to get the shoreline. That's one part of it. And then the second part is getting the elevations. And let me explain how I did it in the next slide. So I'm not going to go through all of these. So my goal was to meet the USGS requirements. And this particular slide basically talks about different requirements laid down by USGS. Okay, so for rivers, 100 feet or more wide rivers need to be hydroflattened. Typically, we even now, like when I'm in industry, we actually do anything that looks significant. So even we do some rivers that are narrower than, and then ponds also, ponds or lakes, we have to hydroflatten the surface. So here's a schematic diagram showing, LiDAR pulses interacting with ground and the trees on the left side, and bottom of the bank, and that's the water surface. So typically we'll have very few points on the water surface. linear mode LiDAR, we have basically very few and uncertain points on the ground surface. So the goal here was, how do I get this elevation and how do I get this location on the side, and how accurate can I be? Let's take another figure here. So basically, I developed something called as base virtual water surface. You can see the dotted blue line based on the few points that were there on the water surface. So it was an iterative process that would go cross section by cross section and basically find out these elevations. Now, just knowing that elevation is not enough, because there are going to be outliers in the data. There are going to be issues in the elevations that I'm extracting. So how do I take care of those? And that was done by applying filters to the data. And once that elevation was obtained, I again, this is based on several tests, I decided to raise that elevation by 0.5. So if you see this IVWS, which is virtual water surface, and that was used, and basically using that, the bank lines were extracted. So that's the overview of the whole thing. Again, I will not go through the whole step. But again, virtual water creation, that was one part of it. Then continuous bare ground surface was another part of it, and then getting the bank shoreline. In the process of virtual water creation, that's where even the elevation of the water surface was extracted. So once I have the bare bank shorelines, then the virtual elevations were applied and basically hydroflattening as well. So both a little variation was there for the single photon LiDAR, because as I said, it penetrates water surface. So I think I didn't have that. So a slight variation, and I was able to perform a similar task on both the LiDAR sensors. So here are my results actually. So you can see the red one is by the vendor, which was manually extracted. Green one is using raw points, and only class 2 points, which are the bare ground points, is the yellow line, which I was getting. And you could see that, some places you could see that it is more aggressive. It's getting to the ground much more. But most of the time, you can see that the yellow line follows the banks very well. Even taking care of the vegetation and other lines. So then that's the accuracy assessment. I did like a GPS survey along one particular portion of the study area, and basically compared the values. And these are basically different water surface elevations, as I said, 0.5, 0.4, 0.6. And we can see that, the mean difference about half a meter, which is reasonably good compared to like the vendor method, which was 1.2 meter. Compared to the GPS, basically, how far were we from the actual shore. Now, there were time variations during data acquisition and the GPS. So the portion of the area that I studied was considerably steep, so that it won't basically cause issues due to time variation. Moving on, I developed another method to get the shoreline. And this is using alpha matting. So alpha matting is basically, you can see me now, right? And anything outside me, beside me, is all blurred. This is alpha matting. So subject and background, right? So I did the same thing with our data set to see if I can get the shoreline. The purpose of developing this method was, this is a probabilistic method. So it will give us pixel by pixel probability of how good the pixel belongs to foreground or background. And in here is just an example. So the white portion is foreground, black is background, and you can see that's the alpha matting output. And based on the probability, you can get the basically different level of probability. We can get a profile, something like that. So So what is alpha matting is a process of extraction of foreground objects from image, and there are numerous variations of this model, and I tested like 4 of them in on shoreline. So over here, I did some modifications. Obviously, I didn't directly use alpha matting, so we need to adapt it to our geospatial data. So the way I did it is basically over here. You can see we have lidar data, the DM, and I created slope map. Using slope map, I replaced on the ortho images, replaced wherever there is a flat surface, basically, assuming that's water surface. Replaced it with 0 angles. So that cleaned up my water surface where there were hanging trees and things like that. Then we had, I was looking at 5 layers, basically, red, green, blue. And then we had the LiDAR elevation and then the slope of the LiDAR, which I felt like are contributors to the shoreline. And now, how do I use this? So I performed PCA to get the maximum variance in the data set. So you can see these are my 5 components, and I use the first 3. I use the first 3 using alpha matting. So this is the first 3 combination over here, performing the foreground background manual assignment. And this is the probability figure, which is showing me that 1 is that it's water and 0 is non-water. And where is my shoreline? Basically, at different level of confidence, you can see there are different lines that I drew. So I believe it came up to 60% confidence, that 60% probability that a particular line was a shoreline. You can see that when displayed, came out like this. Again, I deliberately had this in my paper because there was a break in my data set at that particular point. Therefore, I got that sharp edge. Other than that, you can see followed the shoreline very well. So I'll take a, so from here, I'll talk about the work that I did on in steel mills. Okay, so I'm pretty sure, like, you know, most of you, I mean, most of us like have a similar background. And for me, when I started working in this project, it was a very different experience altogether, because I got to see what happens in steel mill. Who goes into a steel mill on a regular basis, right? It was my first time, and I was so much surprised. I saw so many details. So the owner of the company is Mike Falk, and Nate and Davis were working for him, and I was a consultant. And my goal was to help them basically automate what they were doing, because these mills can extend like almost two miles long. Okay, and in that they would do scannings, and now imagine the amount of details that they could get. They were using terrestrial scanners and tying up the data and processing the data. It was such a great task. I mean, they could find very small things in the entire area, but how do you find it efficient? And that's where I came in. So just an overview here. I mean, they would get a lot of iron ore, which they would melt and convert that into slabs, something like this. And these slabs basically would get onto, like, you know, they would make it molten hot and again pass it through rollers. Okay. And what these rollers would do is basically thin the sheet as I said, it is like 2 kilometers long. So it starts at one end and it goes to the other. And while it is going, it is pressed and pressed. So, and it, I think around like this, about 15 centimeter would come down to a few millimeter over that entire stretch. It would get pressed over and over. Okay, so just one more figure here. So you can see, you know, hot slab comes out of it. That's the cold slab basically gets in, hot slabs comes out, and then, you know, it starts rolling, and these are the rollers. Keeps on rolling, and then at the end it is coiled. So these coils are something that we see on highways. a big trailer carrying these coils. And so there is very, I'll explain why this is very important, what goes on. So there were three things that we mapped here. One was this roller, okay. Then we also developed a method to map it efficiently, basically. The girders and the rails. So let me explain again. This is one of the view. This is using the scanner actually. So you can see how long it goes, and this is just one part of it. And the hot steel would basically start rolling, and you can see the rollers are motorized on one side, and these wear and tear. There is a lot of wear and tear to the rollers also. Now, what happens is that the motors, they're spinning on one side. The steel rolls on it, but what would happen is that if the diameter is not precise, you're going to cause friction on the steel, resulting in degrading the quality of the steel. This particular mill was ArcelorMittal mill in Indiana, and the steel would be used by automotive industries like Tesla or GM Motor or other companies would use that steel. So it has to be of very high quality, and therefore these rollers need to be mapped, or basically manually they would check, take tactile methods of determining if there is erosion on those, and they would then replace those rollers. Okay. Now, goal here was, can we do it automatically, or how good can we do it? Okay. And so we basically scanned the whole thing. Okay. And then we started working. Okay. So this is the roller, basically. That's how it gets carried out and moved to a location and replaced. Okay. And it wears out. I mean, that's going to. So uneven roller, different speed, friction would cause problem. Uneven roller, tilt could happen. So what if there is a tilt, in the roller? There's so many factors, so many things that could go. And overall affects the quality of steel, right? So how do we take care of it? So tilt, radius, diameter, uneven surface, elevation of adjacent roller. Is one taller than the other, or are they all on the same level? If there is a slope uphill or downhill? A very small slope can cause problems. Okay, so this is just a 3D view of the points. Now we were scanning on one side, right, and then the other side, as much coverage as we can get from the data set. Now, manually, the software that the company was using, called I don't remember the whole name, they would try to model this using a cylinder model. They would try to fit a cylinder to the data point and then try to come up with if things are okay or not. So the way I approached this is quite different. So first thing was that there were these were like hundreds of them lined up next to each other. First thing was finding where they are, right, and then trying to model them, and then trying to find all these deformations in the surface. So this is my workflow basically. I got the point cloud into MATLAB and voxel, basically 3-dimensional cells where these points would be, and I looked at the data across, so that if there is a certain number of points, I would say that it is a valid voxel. Performed FTT matching to detect the roles. So just to find where these roles are in the data. Okay, and I'll show you some diagrams following. Then once I know where the rollers are, then I take the point and then I perform circle fit to the data set. And then I basically slice the data over the length of the roller and get the profile of the entire roller on how good or bad it is. Okay. So circle parameters were defined. It was refined until a good fit was obtained. And then color mapping was done, and roller top mapping, and roller center line. So there's an example. So I'm just showing you 5 right now here. So a 5 roller set would look like these from the side, and voxels, next slide, I believe. And so these are voxels here. And you can see white area is actually where the matching was not done, and it failed, not failed, basically it removed it as outliers. So you can see this points were shortlisted saying that, okay, there is a possible roller in this area. And once I had that, then basically circle fitting was done and allowing the circle to fit properly so that we get the actual radius of that roller. Okay? And points within 0.2 feet were retained, and you can see the green points were retained, and all the rollers were actually extracted like that. Now, once these were then extracted, so you can see this is basically radius variation, how the diameter of the radius of the rollers vary. So you can see this is there's a larger roller at this point, smaller than going down. So these are wearing out. Maybe that's a new roller. That is. Okay. Then this standard error was reported. So this is deformation mapping to show where things were eroded and where things were accessed. So the red areas were erosion. Erosion reference to average was red area, which is this one here. And the blue area was basically access. So you can immediately see that this roller was not getting eroded uniformly. And green area was okay. This is like a span of I think 20 some rollers that you can see, and you can see different rollers highlighted in different ways, showing a different amount of erosion around the rollers. That's the average top surface elevation. Where was the top surface again? Because you don't want to have the rollers climb up or go down, you want to have them flat. Okay. This is the profile mapping. Now, obviously, there were some outliers sometimes, like this, the one that you see, but you can see how the profile varied along. So, a slice of, I believe it was 1 inch, every 1 inch the roller was up, and it showed how the roller was that particular case. Like you can see completely a tilted roller here. Whereas over here, you can see this portion getting eroded. This is okay, that is okay. Right. So that was roller mapping. Then I did a couple more that was rail mapping and girder mapping. So, so in a crane, in a steel mill, what they have is a system like this. There are girders on the side, and this is called as a gantry crane or a girder crane. Basically, it had wheels on the side, and it keeps on moving. So in the span of like 2 kilometers, there were like 3 or 4 of these cranes that would move back and forth carrying heavy loads like this. Okay. Now what would happen is that over the time, it would things are going to degrade, right? The rails are going to buckle, the crane is going to have some kind of deformation, and also the girder is going to buckle. Now, traditionally, this is again was done using manual measurement, and believe me, there were so many issues that they could miss easily. The mill environment is very hot, okay, and in that to do that kind of work is very tedious. And what Falk Engineering was doing was amazing because they took out that in office in the mill work and took it to the office in a comfortable environment. So they would scan the whole thing at a very high rate, and then again they were in problem of how do I process the data. Now they're getting the data, but they don't know how to process it or extract it. So you know the crane supports the gantry crane transports steel or heavy material, periodic maintenance and repair, risk mitigation. I think there was one incident in India. These mills are in Jamshedpur, Jharkhand area, and there was a big incident over there. I believe that a molten core was carried, that the crane was carrying, and it basically buckled, and there were a lot of fatalities in that particular mill. So things like that could happen. Furthermore, these mills work 24/7, and if they have to stop, like their loss per hour is significant, very, very high. So they can't really afford this. So therefore, these things that we were doing here was very, very useful. Both in terms of material property and also loss, like any kind of material loss. So currently, manual measurement and laser scanning was there, but still manual extraction was going. So here's my workflow over here. The first part was getting the girders map, and basically point cloud, again MATLAB, my favorite. Image processing to do plane detections. Now I'll show you why plane detections, because these girders had stiffeners and joints, and the area between them was flat. So basically detecting them was first part here. And once I have them, again I did the same thing. How frequent can I check where the buckling is taking place in the data set? Okay. So, and then color mapping and vacuum mapping of each panel for deformation. So image processing, I'll skip through this. So I'll show you what happens. So this is the standard, like one girder here. You can see a joint here, and then there are stiffeners. Okay, and the rail would sit on top of this. So getting this was one task. Okay, once I have them, then finding how. So this would be a I section basically. There is a bottom of the flanges on top and bottom, and the web in the middle. So again, deformation, how things are deforming. So -1 over here, you can see high deformation in this particular panel. Then the actual slices and how do I get them? So I used a template of a data, I section, and try to get template matching done at every section. So I'll show you that. So that's the actual point cloud, and you can see the nature of it because the scanner is somewhere down, right? You don't get points here, you don't get points here. Now, using a template data like this is used, a very simple straight line basically, and mid, bottom, and top. I don't see a top button here, but there were 3 levels here, mid, high, and low. And they were used to basically determine how these points are moving in vertical, horizontal, and both in X, Y, and Z. Okay, but after fitting, so this was fit onto this here, and once I know where it would fit, we're using least square adjustment again. So you can see, so those were called as interest point basically, IPs, and train distance were computed, and least square adjustment was done to fit that data, the point cloud. Once I have them, then you can see how the fitting would look like. This is fitted data on top of it. Then at every section, I would go ahead and map it. Again, it was like almost 2 kilometers long. And a fin transformation matching. Now, different methods were experimented to see how they work. And then this is Y direction. So from center of the bay, where is the web? So you can see it is steady, then going away from the center, coming towards the center, going away from the center. Pretty uniform here, going towards the center, again coming back, and then going away. So what would happen is that if this is just one side of the crane. If both sides would go away, basically the crane could collapse, right? And if it is too narrow, the wheel would cause friction. So this is a very important data for the mill. Okay, and you can see all 3 of them are shown here: top, mid, and high point of the data set. Then there were rail extraction, which is on the top of the girder, and you can see that is just the portion of the rail that was available. And so again, the same approach was used using a template data. And so that's the template. Again, we're looking at these two important points and performing matching. So least square adjustment, again, you can use this and get that data fitted here. You can see this kind of fitted in that here. And once I have that, you can see that is the fitted data here. Once I have that, I can get these important points, rail top and rail center, and map the whole thing again. Okay. There were some moving averages used to filter out outliers, and data points with 95 confidence were retained. So you can see here, there's the raw data. You can see, what were these? These were basically where the rail would get connected. That's where the method would fail because there was a joint in that particular location. Okay. And so you can see I believe this is in feet, inches, my bad. And you can see the number here. So every connection, and so that was removed by using a filter. And so this is unfiltered and this is filtered, and you can see that this is elevation, and you can see the crane is going, the rail is actually heading up pretty normal over here, but a big drop at a couple of steps. So again, very important information for the steel. This is horizontal distance, again, how the rail is away from the center line. And you can see, it's kind of going away from the center line at a couple of locations. So they're very important and very informative for the mill. So this presentation described the methodology for gantry crane and the rail monitoring, and two approaches were developed. And actually, within each approach, there were different smaller techniques that were tested out, and methods were to get the results. So on this particular work, I actually have a patent on this, and that patent is, I shouldn't say we have a patent on this, and that is basically what we developed was a dynamic real-time 3D monitoring system. So we mounted a scanner on this, and as this crane would go back and forth, it would basically map the whole system in live, basically. There was a live data feed. So with that, that was the application, basically. That's where we got the patent of this particular. So with that, actually, I went quite fast, I believe, but I am at the end of my presentation, but I can go back now and slow down, I think, and answer any questions if you have.
Thank you very much, sir, for your presentation. Initially, we have a technical issue in connecting with the platform. That's why the delay happened. Now the session is open for questions. Participants, if you have any questions, you can please ask or type in the chat box.
Did you guys hear me? Hello?
Yes, it's audible, sir. It's audible.
Yeah, that was. Can I, Rimisha?
Yes, sir. Yes, sir. Yes, sir.
Okay. Yeah, that was the presentation. In fact, my question is, this technology probably like what you have mentioned, maybe limited to a laboratory or like an industrial setup. Whether we can use this technology to monitor the deflections of the bridges, the railway or the road bridges. Can you throw some light on that area?
Yeah, so again, my company that I was working with, Falk PLI, was interested in bridge monitoring also. Now, there are two approaches that he was thinking about. So right now, in US, actually, mobile mapping scanning. So the mobile mapping scanning is where we have the laser scanner mounted on a vehicle, and that vehicle basically goes and collects data. And you get a lot of point cloud over the entire area. So what our team was thinking is, can we use that data and report findings? Okay, that's one possibility. The second thing is that if you have a scanner, if anybody basically take the scanner and scans one bridge, but time-wise, it's not very efficient because you're spending a lot of time just for one bridge. Using the mobile mapping was the approach that we decided to go ahead, but we didn't really, because Fall PLI is completely into industrial mapping. So I did try to reach out to some companies in India where they could use, like for example, automotive industries would have a crane like this, or basically many manufacturing company, major manufacturing company would have a crane. So that is somewhere things could be easily used. This particular model can be used.
Yeah, thank you, Sagar.
Thanks. Was I clear in my presentation? My voice was clear or no?
Yeah, just okay, just okay, just okay.
Okay, okay.
Sir, I have a question in your initial slides. I made a coastal erosion, how to estimate the erosion extent using the AS.
Okay.
In the state of Kerala, we have issues like the coastal erosion in several places, like Chengalpattu, the Chellam and
I'm getting a lot of echo.
Sir, is it audible? Now, is it audible, sir?
Yeah, it's okay.
Yeah, so I have a question regarding from your initial slides on coastal erosion. In the state of Kerala, we have a lot of problems on coastal erosion. So we are finding out the extent of erosion in several places like Chengalpattu or Chellam. So how many years of data we need to get for a proper prediction of the extent of shoreline? And also,
So we had, I believe we had 5 different shorelines. You know what? This paper is actually available.
okay. So for estimating the sediment transport, that may be erosion or deposition. So how much years of data we need to collect for the optimum accuracy?
Well, I think you can, I mean, even if you have 2 time frames, that is like not going to be long term, but you can definitely report a smaller time frame. But let me show you how much. Yeah, this one here. So this is a coastal change analysis paper. And I believe we had like 4 or 5 shorelines in this particular project. And so you can see very similar data. So, and what we did was we were trying to correlate environmental factors in this particular region with the erosion rate that we observed in that particular location. Now, there were some issues also with the data set. At some points, we thought that it may not be that accurate, but it is what it is, because we can't really somebody has acquired a shoreline 10 years ago with the recent technology at that particular time. Okay, so we just have to use that data as a reference point and do our analysis. Does that answer your question?
Yeah, yes, sir, yes, sir. Thank you, sir.
Okay. So in general, I'm curious. I have been out of India from 2001, 2000 no not 2001, 2004, and I've followed Indian research very closely. Nisha is my friend, and I'm in touch with her always, and many more friends actually in India. I was curious on how things are right now with so many remote sensing satellites that are launched by India. Is it still the same? Like you have to, how is it easy it is to get the data? Like back then when I was a student, I didn't see any IRS data. I mean, yeah, to be frank, I think the data that I had was again Landsat at that time, which was easier to find rather than IRS. So how is it right now?
Since we have an open platform, we get the data for the but for more accurate data, we need to approach the governments or to pay and all. That's
Oh, there is an open platform.
yeah.
Oh, okay, good. I see. That's
Like
nice.
that we can use. But the problem is for more accuracy of data, for example, for VM, we are using, we need more accurate data that is very difficult to get.
I see. Okay.
And also the government agencies are also not much practicing in doing JS and all this because of this irrigation and all. They are doing this constellation manually, how much that extension or they are identifying. So if we are using these technologies, that will be great. Better. That will be
Yeah,
better.
I didn't mean to say it in a negative way, but I was curious to know how it is right now, because I
Things
think
have changed.
yeah, okay, yeah,
Things
because
have
the
changed.
more students get access to the data, more innovation will happen, and more growth will happen basically. So
Actually, we have like Bhuvan platform. They are providing a lot of data that has archived in the previous years.
okay.
So previous, as you have told correctly, when I was a student also, we have to get these details at a very, we have to pay a lot of money to get the
Yeah,
data. But things have not changed much. If you want a high resolution image, we need to rely on foreign satellites. That will be better because they have a very good collection and payment. Price is also a little high, but we have good sort of research set, and those satellites are having very good resolution, and that are not available. Like if I want an image of 2023, I need to procure it, and if it's for 2000, we can get it free. So there is like a little constraint, but data is more available
right.
rather in the previous years.
Oh, that's good. Yeah.
So if we don't have any further questions, we can we can close the session, and I would like to give an apology because there were certain technical issues, and the video and audio were not got stuck
Oh,
up.
no
I'm
problem.
apology for that.
No problem. That's
Okay.
fine.
So we will move on to the vote of thanks, and it will be delivered by Ashik, junior scientist.
Okay.
Thank you, sir.
Thank you.
We have been privileged to gain deep insights into the topic alignment mapping of structural members and rollers in a steel mill using terrestrial Lidar point cloud. Delivered by our distinguished speaker, Dr. Sagar Deshpande. Your expertise has not only illuminated our understanding, but has also inspired us to look at time-efficient method to extract and model rail and girders used in the steel industry using the terrestrial Lidar point data. We truly appreciate the time and effort you put into for preparing and delivering such an engaging talk. We'd also like to extend our thanks to all the attendees for your active participation. We hope that you found the information presented today both informative and inspiring. We are very much thankful to our director, Professor Sagar Matthew sir, for his constant guidance and support in shaping this wonderful event. As we depart, let us carry forward the knowledge gained and connections made. May the insights shared today fuel our curiosity and drive for excellence in the field of GIS. Once again, I'd like to express our sincere thanks to Dr. Sagar Deshpande, the NATPAC team, and all of you for making this technical talk a great success. We look forward to much more enlightening sessions in the future. Thank you and have a wonderful day.
Thanks.
Thanks,
Thank you, sir.
Yeah, thank you. Bye-bye.